Greetings to all. I'll be demonstrating our project Brain Heart Connection for Psychological Health. Our project is based on a dataset called Dreamer dataset. The Dreamer dataset is a .mat file, so we use SciPy library to load it to the Python model. The dataset contains EEG data, ECG data, and subjective ratings. The first function of our model is to preprocess and feature extract EEG data. The preprocessing of EEG data consisted of extracting the maximum of PSD, that is power spectral density, for EEG signals for three bands theta, alpha, beta for each of the 14 electrodes used. The library SciPy was used for filtering and PSD extraction. The next function was to preprocess ECG data. The preprocessing for ECG data was done using library called NeuroKit2 using ECG process method for preprocessing and then extracting the features with ECG interval related method. The features extracted were the mean heart rate and various heart rate variability metrics. The next function was the participant data. The participant data is created using age, gender, video ID, video name, target emotions, valence, arousal, and dominance values. This is visualized in the visualization. So this is a plot across mean arousal, and mean valence, which plots the based on the ratings given by the participants to each of the video clips. There are nine target emotions chosen: calmness, surprise, amusement, fear, excitement, disgust, happiness, anger, and sadness. After the participant data was created, we were interested in training a classifier to detect stress. But the paper written by Wien and Lachiri in 2017 told that automatic emotion recognition and stress detection was has relied on different models of emotion. So initially we had made the participant data based on the dataset paper with a target emotions, but later we concentrated on distinguishing calmness from two emotions on opposite side of spectrum, which is anger and fear. So this is done by the function select target emotions. Now, after this was done, we tried to get an idea of how the classifiers would perform given biosignals data from completely new people. So we evaluated the classifiers using 10 group tenfold cross validation, with the groups being the participants. This is visualized in this visualization. So the training set and validation set always consisted of data from separate participants. So this made sure that all the data was considered and none of the data sets overlapped with each other. The y-axis shows the film clips, the video clip names, and the x-axis shows the number of participants. Once this was done, um, we chose nine classifiers based on a script from scikit-learn documentation. This is visualized in this visualization, which is a score versus prediction runtime for all the cross validations and classifiers. The classifiers chosen were nearest neighbors, linear SVM, RBF SVM, Gaussian process, decision tree, random forest, neural network, AdaBoost, and Naive the accuracy and runtime of these classifiers is shown here. The accuracy of AdaBoost was the highest with a mean runtime of around 3.9 milliseconds. If the mean runtime is high or mean runtime needs to be low, then nearest neighbors could be chosen with an accuracy of 87%. Once the classifiers were classified, the next step was to relation between EEG and ECG. This was first initially visualized using the different heat maps. So this heat map here shows the relation between valence and arousal of different features of EEG and ECG. And the next heat map is a cross correlation matrix between the different features of EEG and ECG. And this shows that there is some amount of relation between EEG and ECG. And this is shown in the form of percentage as well. So only with EEG cross correlation and ECG correlation and fusion of these two, the accuracy is almost in the same level. So that is what we inferred from our model. After we had done the model, we even built a circuit for EEG and ECG. This is shown here.
So this shows the EEG circuit. Coming to the ECG part. This shows the ECG circuit.